Okay, Chitra, now can you
Yes.
please start?
Okay, sure.
Okay.
So, hello everyone. Today, I'll show you guys how to run the molecular dynamic simulation through program NAMD. So, I have included a couple of files which are needed for the NAMD simulation. So, this is the folder that I shared with you guys. So, you may not see some of them, but yeah, most of the file needed I have included in that folder. Some of the files, they are generated during the process. So today I'm going to demonstrate the simulation setup for the protein called 1WA8, which is the tuberculosis protein, which is sorry, which is important for the virulence of tuberculosis. So the main process, the starting point is to
Excuse
obtain
me,
the
Chitra.
structure. Yes, yes.
Are you sick today?
Yeah, no, actually not, but I have some problem with my voice.
Okay. So if you don't feel comfortable, if you're sick, we can postpone the lecture in on Wednesday.
I think it should be okay if you guys can hear well. It should be okay.
Yeah, we can hear you, but you sound like you're sick.
Yeah, yeah, my voice is kind of low or it's getting thicker.
Okay.
I don't know.
No pressure. If you're okay, please do it. If you don't feel quite okay today, we can postpone it.
I think it should be okay. I don't feel
Okay.
any pain or something. It's only with my voice. I think I can continue with this one.
Okay.
Mhm.
Thank you.
Okay. So if I find any difficulties, I'll let you know, and maybe we can uh, continue in the next lecture if I find difficulties
Okay. Sounds
during
good.
this period. Yeah. Okay.
Okay.
So the initial process is to obtain the structure of the protein. Generally, experimentalists, they do varieties of experiments and solve the structures for the protein, especially the three-dimensional structure. They have different techniques. Usually they solve the structures and store them or report them, upload their structures in different databases. Frequently, or most of the time, we use the database protein data bank for our research purpose. So if you go to if you search for PDB bank, go to the home page, then you can search for your protein if you know the ID. So every structure they deposit here, they have a unique 4-digit IDs. So if you know that 4-digit ID code, you can directly search that, or if you know the keyword for the protein, you can also do that. So for now, I already know the PDB code for my protein, so I will simply type it. It is 1WA8 and give it a search. Let me, okay. So it will give you the structure. It will give you the information about the literature, their solving process, and different informations about their experimental procedures. So you can get a lot of informations about the protein itself from this web page. So focusing on this protein structure, it's a dimer. It has 2 chains, and you can see a lot of jiggling structures here. It is due to that this structure is solved through uh, NMR, and they take a pictures or snapshots of different time frames in their experiment, and they superimpose together to get this structure. Actually, I guess they have multiple structures superposed for this structure. but we'll take only one structures for the simulation here. So if we look at this structure, yeah, this is the one structure. If you see here, it's a 1 out of 28 structures. So in the previous figure here, it's superimposition of 128 structures. So we don't need all of them. We only need one structure. Yeah, so we can download this structure from this tab. So we can download the different formats here. We will download the file in PDB format. So I already did this, and we can download this file. So I have already downloaded and download in the folder, in this folder. And I have also shared this file to you guys. You can look, look at this file in the folder. So this is the one. So I mentioned that there are different structures, or 28 different structures superimposed together. So let's see how it looks in the text file. So I'll open up a terminal here in this folder. So I will vi this text file. Okay. So because I already have this one, it saved my file as a one. So there is a small gap in here. So I supplied this pass character to read the gap between this name, or for simplicity we can rename this pdb file or remove this one, and it will be easy for us to read in the vi. So for now I won't change this, but you can rename this for the simplicity. So let's look at this. Okay, it has a lot of header files, a lot of information about the protein, their experimental procedures, information about different parts of the proteins, about the different structures. I mean, the primary or the secondary, tertiary structures can be found here, or the information about the helixes, beta structure, something like that. So from this point onwards, we have the records of atoms. So in the PDB file, the things that we need is from this point onwards. So these are the atoms, and the second column is the atom serial number. So this is the third is atom type. This is the residue type. This is the chain ID. This is the residue ID. So till here is the residue, first residue alanine. And from here, second residue starts in the sequence. So these are the three-dimensional coordinates for this atom. So for this till here, these are the X, Y, and the Z coordinates for this specific atom. And so for every atom, we'll have these coordinates. So we don't really care about these two columns here. They are specified for, they're designated for some occupancy and the temperature factors. But for now, we are not going to use this column here, but they have their own function. Yeah, these are also again the atoms, or sometimes they are also referred as the segment. But for now, they specify the atom here. So this N means nitrogen, carbon, carbon, oxygen, the initials of the atoms. Okay, this was the file. So if you see here, here is a model one. So we saw that it has 28 structures superimposed together. So this one is the model first. So if you search, if you in the vi editor, if you type the slash, then it's a search mode. You can search for the keywords to find that in that file. So I'll simply search for model. If we hit enter, it will search for the models. And if we type N, it will search the next occurrence of that word. So it's model second, you can see model second here. If you type n again, it will take you to the third model, fourth model, and so on. If you go to the end of the file, this is the end of the file, and most probably the last model is the model 28. Yeah, I think it should be model 28 somewhere here. Yeah, model 27 is the last model. So here are 28 models. We only need any one of them, so you can save either simply copy paste or use some Linux commands to save one particular model for the simulation. Yeah, whatever you guys feel easy, you can do that. I already extracted one model out of these 27 models. I already did that and saved it here. You can simply open this file in some gedit and just select and copy paste as you. This is the very simplest, but not the professional way. If you want to do in the professional way, you can make use of the different commands like we read in our class. For example, we can use awk. Maybe if you guys are interested, I can give some demos, but I think it will be much longer. We can do it later if you guys are interested. I can show how to do that, how to save particular lines or save the particular model from that big file. Okay, this is how we get the structures. Now, after we get the structure, now we'll proceed forward to prepare the files for the simulation. So the first step is to convert this PDB file, which contains the three-dimensional structures uh, of the protein. We will convert it into PCF file, which is the protein structure file. And these structure files have all the topology of our protein, which means the geometry of the protein itself. Also, how what is meant by the topology in a while. So first, I want to tell that during the process of solving the three-dimensional structures, generally due to the high flexibility of the hydrogen atoms, so sometimes they cannot record the three-dimensional coordinates of the hydrogen atoms. So these atoms are not listed in the PDB file itself. So in the PSF file, once we convert into the PSF file, it is also to add those missing hydrogens which are not recorded in the experiment. So using certain algorithm, we will add those hydrogen back to the protein structure file using certain algorithms, using certain techniques. And those techniques are based on the charm force field. So since this structure is solved through the uh, NMR technique, most probably they could also have included the hydrogen atoms, but this is not the case every time. So we may not have the record of hydrogen atoms. So we'll see the difference later once we will compare the protein, PDB file before and after after converting it into the PSF file. Okay, so to convert the PDF file into PSF file, we will need VMD. Wenhang and Sinje, they taught us how to use the VMD and the Chimera to open up the files and do the different manipulations in the protein system that we're interested. So I'll simply first let's check the structure of this PDB file. This is one model out of 28 models. So you can save any one of the 27 models, doesn't matter, because at the end of the day we'll simulate and it will change its states to come to the minimum position, and it will run the simulation to equilibrate the system. So for the initial structure it's okay. Okay, that was our structure. Now let's open the VMD. You can type, if you have already installed the VMD, so you can simply type the VMD to run the VMD program. So I have included this text info file where you can get the information about if you information how to install NAMD and the VMD in your computer. If you haven't installed it, you can look at this reference to do that. Oh, what happened? Oh, oh, sorry, I think I override this with something. You can try the link in your original file. I think I changed this file, change the link here. You can double check the original file there. Okay. So after that, let me open the VMD here. So we don't have to load the PDF file here. Simply go to the TK console here. Yeah. Remember that we are in this location here. So if you want to double check, you want to do in the terminal, you simply do the pwd, which is the print working directory. Then it will give you the directory you are in. So this is our working directory here, where we have all the we have all the files which will be needing throughout this process. Okay, so here we have a let me find the proper file. Okay, this one. So so this file is the file which helps us to convert the protein PDB file into the PSA file. Let's look at the file. Look at this file to see the different commands that are being used for this process. Yeah. So this the TK console is the interactive mode. So we can type different commands. It is compatible with the TCL scripting. So these commands are in TCL scripts. So it is it have a interactive mode with the TCL scripting. So the first command is simply we load our protein, which is this file, this PDB file. Then to generate the protein structure file, we need a package, and this is the name of the package is psfgen, and we need a topology file, and this file is also at the same location somewhere here. Where it is? Here it is. Yeah. So this is the topology file that I was talking earlier. So this contains all the information, the geometry of the system, geometry of our protein. It contains information about charges of the atoms, their masses, and different things. So first, let's look at this file. What it contains? What sort of information it has? So if you VI this file, these are the different headers files. These are the informations about the masses of the atoms, and they have different sections for like the nucleic acid, the protein, and different other ligands or different other non-regular fragments of atoms or molecules that may have while they solve the three-dimensional structure. So the main information starts from this portion. So if you see, this is the information of the alanine. So the protein is simply the compilation or the polymer of the 20 regular amino acids that we have. So the topology file contains all the information about the residues and their connectivity, the connectivity of the different amino acids through the peptide bonds. So if you look at the alanine residue, this is the chemical formula for this alanine, and these two ends are the connecting bonds for the other residues. So these are the different atom entries. These are different atom types, and this column is this is the charge on the atoms in the specific atom. So if you look at nitrogen, here is the nitrogen, and this is the atom type, especially for the charm force field naming style. This is for the PDB file, and this is for the charm force field file. They will name nitrogen as NH1 in the charm force field. Likewise for other atoms. So these are the different atoms, information about the different atoms in the residues. So they will also have the information about the bonds between the different atoms. If you see here, the atoms are connected through the bonds here. So these informations are for bonds. Also, I talked about the missing hydrogens. They also make use of these informations to guess the position of missing hydrogens. So once we create the protein structure files, they will protonate the PDB file using the information provided in this topology file, this file. Yeah, similarly, these are the information for arginine. So you can navigate this file and see the informations, what are the different informations provided in the file. Also, you can, if you are interested or want to learn in details, you can give a quick Google search on the topology file for the NAMD simulation or topology file for charm force field, then they'll give you the detailed informations. So for now, let's simply convert the protein PDB file into PSF file and see what kind of file is generated. Generally, the information in this file, they are mapped into the PSF files. So which is needed for the calculation of energy or for the calculation of the dynamics during the simulation. So we need all this information for the energy calculations and their position and velocity calculations under the force field, under the charm force field. So these informations are very important for those calculations. So I'll quit this file for now. Okay, so we were here. Okay, so that was the information about the topology file. So they use certain alias for certain atoms here. Or they create the alias for histidine as HSE. Actually, there are the different states of histidine, and for this stage, we alias make alias of histidine as HSE. Similarly, for the atom ILE, we create this because due to the naming style in the charm force field. So once we create this alias, it will know that this atom it has to be read as KD. So the force field will know that. So to convert the PDB file into PSF file, this is the main script manuscript, let me explain a couple of lines. The lines here, what they are saying here. So first we load the PDF file, then we loaded some packages and the files, the force field we are taking into account and creating some aliases. Then this line is to select this line is selecting the chain A and the protein. So I forgot to tell you that. So in our system, so there are two, it's a dimer. So first one, this this fragment, let's say this fragment has the chain ID B and this has the chain ID A. So based on your system, maybe you want to work on the different other protein. They may have different chain IDs. So what you can do is, let's say it has some other chain ID, let's say C, then you can give a selection as a chain C and protein. And based on the number of fragments, you can make this different mm, block of codes for different segments you have or different fragments you have in your protein system. So for now we have chain B and chain A. We have two fragments. So for chain A, this is the, okay, let me separate this, okay. This block is from 14 to 19. This is for chain A, fragment A. So in 14, we select chain A and chain A and the protein. And we write that selection to a PDB file, a.pdb file. We make a selection, then write a PDB from that selection. Then this is to assign the segment name. Yeah, this will assign the segment. And segment is also, what is the segment in the PDB file later. So this is for chain B, same thing. So line 28 is for guessing the hydrogen atoms, missing hydrogen atoms. Uh, and this will write the PDB file, which will be protonated, which will, this is the output file we are writing, which includes the atom entries we have, while atom entries in the downloaded file, and the hydrogen atoms are being included. We're writing that file in this line number 29, and 30, line 30 will write the protein structure file. So first let's run this file and see the output files. Okay. Okay, let me go to the VMD. Hmm, What it is, let me find the console. Okay, here it is. You can also do the list here. We have a psf.tcl file. We simply source this psf file. So if you source it, it will write the output files that were in the last two lines of our script. So let's run this. Yeah. So it is successfully run and it has given a lot of informations. And let's check the output. And I'll also like to open the, okay. So if you look at the output, it generated a.pdb file, which was written in this line 15, and pdbb written in this segment here. So after that, we assign the segment B and segment A for those respective chains. And at the end, we guess the hydrogen coordinates for hydrogen atoms, and we write the whole PDB file combination of these two fragments, chain A and chain B, into the single protein file with the hydrogen atoms and write a protein structure file. So the output were A and B, protonated A and B, these are segments. We are not going to use these files, but in the process they are generated here. We are interested in these two files, this file and that file. So let's look at these files. Mm. Yeah, so it will almost remain the same, but hydrogen atoms will be added. So we'll compare the number of entries here. I think it's solved through the NMR process. So I think they have already included the hydrogen atoms, but let's see, let's compare and see what happened. So this PDB file, the output PDB file will look almost the same. And this was the segment being written here. And let's go down. Yeah, and for the chain B, we have assigned a segment B here. And all of the information will remain the same. And but the hydrogen atoms will be added. So let's compare this file and the original PDB file that we used. Okay. Okay, let's go to the end of this file. So it has almost 2822 entries of atoms here. So also go to the end of this file. So there is a certain difference, and that difference is from adding of hydrogen. The number of the atom entries in this and this file are very less. I think it is due to the fact that in the experiment they also have the record of the hydrogen atoms, but this will not be the case in every system. If the structure is solved from, let's say, X-ray or some other crystallographic methods, they may not have the hydrogen atoms. And if you compare these two files before and after the conversion of PSF file or the protonation of the file, I think the number of atoms will be almost doubled. But now we don't see that much big difference here. I think it's due to the fact that it's being solved through the NMR structure, and it is solved through the NMR technique. And NMR technique are used to solve the highly flexible protein systems. Maybe it also they were also able to include the hydrogen atoms in this file. So in that sense, we don't see the very big difference, but still some of the hydrogen atoms are being added. Yeah, if we not include this end and the some lines which are not designated for the atom entries, there is very subtle difference. Though there are some hydrogen atoms being added, there are certain techniques to uh, professionally see what new lines are added. So there are certain techniques. I'm not going to talk about that. Maybe we can do find the like exactly the exact difference between these two files. So okay. Okay, let's now look at the pro.psf file. So you can name anything. You can name the output file as per your wish. So I named them pro.pdb and psf. You can name it anything for this initial name. So this is the PSF file, this file. Yeah. So it will contain all the information about the protein. So for these entries, we have charge and the masses of the atoms here. So if you scroll down, you'll find these information for all the atoms we have in our system, in our protein. So this entry is for protein and the the charge and then the mass of the every atoms we have. So from here, bond information are being read here as being recorded here. These are the bond information. So before I go to here, I want to show something. Maybe this one. So in the protein system, we'll have the geometry will look like this. So for the atoms, like for the neighboring atoms, this is the bond. We suppose that they are connected through certain bonds like this. So we have if we have a three atoms connected to this kind of bonds, and we'll have a certain angle between these two bonds. This is another geometry, and this one is the another geometry. This is the angle geometry. This is the bond, and this is called. Let me. I think this is called torsion or something. I don't remember exactly. It should be. Oh, sorry, it's a dihedral. It's a dihedral geometry, and this is the improper geometry. So if you want to look at the details, you can look through this paper what this different geometry means. So generally, the combination of these geometries between the atoms will construct our entire chain of entire protein. Yeah, we'll have this sort of geometries, and we need information about this length. What is the the bone length? What is the mass of these atoms? What is the charge? What is this angle? What is this the torsion? What is the like how by how many angles it is twisted? And what is the fluctuation in this plane and this shift? So we need all this information to calculate the force or the energy in our dynamics. So we we need all these physical properties, and these properties are included in the PSF file. So this is for bond. Let me open this file side by side here. So these informations are for different bonds that we have in between the atoms. And if we go further down, oh, yeah, these are the information for angles for different combination of atoms, so and so forth. You can go down and see the information for other geometries. I'll quit this one. I think I have also included the link in that file where to look at the information about these files, or you can simply look at this paper, this article, to get the deep informations. So so once we created the protein protonated PDB and the structure file, PSF file. Now next step is to prepare the configuration file, the parameter files that we'll be needing for the simulation. Okay, so now let's look at the parameter file that we'll use in the NAM simulation. So this is let me show you the configuration file. It should be this one. Yeah. Yeah. So this is the configuration file, which contains a lot of parameters to calculate the dynamics of the system. And the dynamics is governed or ruled by the force field, and that force field is this one, uh, which contains the parameters for calculating the and different energies and velocities or the coordinates during the dynamics, something like that. So we'll also look at into this file. So talking about this force field, they have a different versions of the force field. Currently we are using uh, version 27. Now they have version 36. They are the updated and new force field. You can download those force field from their web page. So if we give a search for the charm force field, then we'll get a lot of information about them. So maybe let me give a quick search. Yeah, somewhere here. Yeah, these are the latest force field that you can get that are optimized and newer versions. But for this work, we are using version 27. Okay, so let's talk about the parameter file or the configuration file for the NAMD simulation. So this is the structure file, which is the protein structure file that contains all the geometry and the topology of the file. So this is the coordinate, which is the protonated PDB, and they are at the current location. They're in our working directory here. So you can, if they are not in the current directory, you can give their absolute path for them or the relative path. Either way, it works. So for the simulation, we'll set the temperature to be 300. So based on, we can modify this temperature. So based on your requirement, based on our requirement, we can change this temperature. So for now, we are using the standard temperature or the room temperature, which is 300, and the unit is in Kelvin. So in line 19 says the outputs file we generated by the NAMD program will be in this directory, out directory, and the initials of the output files will be named equal. So, or simply we can either we can even we can save the outputs in the current directory itself, like this. Oh, like this. So since there will be a lot of other files, we don't want to mess our file system. So it's better to uh, direct our outputs in a separate output folder. Okay, so but before running the simulation, we need to create this folder by ourselves. This directory, out directory. I have already created this folder here. Yeah, this line 21 says this is the first time state. It's self-explanatory. So during the process, the first step will be 0, and we'll also have the last step from till which we want the simulation to run. So that entry will be at the last. So this line 29 is about the force field. We turn on the force field, and this is the all the information needed for the force or the energy calculation. So this is the parameter file. So let's quickly look at this file, what it contains. Okay. So if you scroll down, yeah. So this parameter file or this force field file contains the information about different potentials that are included in during the simulation. So again, if we look at the this file, this paper, I think they have included the different potential terms that are being used to calculate the energy. Let me find it. Mhm. Yeah, somewhere here. Yes. So the there will be different energies interacting or different potentials interacting in the systems, and in the NAM simulation they include these kind of potentials to calculate the energies. So they are the bond, which we already shown what is the bond there. So this potential is due to the like change in the bond length during the simulation. So this, I think, if you go here, yeah. So this is the bond, and they can, during the simulation, this bond length can increase or decrease. So due to that, it will have certain potential between these atoms, so that energy can be calculated from the potential of that kind is defined here, defined by this physical formula. The formula is given in here. Here K is the constant, some physical constants. So this is for angle, this is for dihedral, this is the van der Waals, and this is the Coulombic. These three, the first three are the bonded energy terms, which are directly linked through the bonds. But these last two energies are non-bonded energies. So um, I think Dr. Lee already explained us in his lecture about the van der Waals and the Coulombic energy. So they are not directly linked to the bonds, but their interaction is through the charge interactions. The Coulombic it's simply it's coming through the Coulomb's law, and this is coming from the induction of charges when two atoms are bring in a close vicinity of each other. I think if we get confused, we can refer to his lectures for these energy terms. Yeah, these are the different formulas they use to calculate the potentials. Here is the van der Waals energy term, potential, and this the Coulombic. So in the process, in the NAM process, NAM simulation, what happens is they will calculate all these energy terms, and let me see. Yeah. So, and the dynamics will be calculated by this relation one. So U total is the total potentials that we have in the system. And if we do the integration, we'll get the force. And we know that force have the second order derivative of the position. So from here, we can get the position or velocity from this relation. Once we have the potential, we can get the position and the velocity at different time frame of the simulation. This is the basic concept here. So from here, we will record the dynamics of the atoms. Using this relation, we'll find atoms or velocities or different other parameters can be calculated from this relation once we have the total potential here. Okay. And these potential are governed by this force field. Yeah, we have all the information about those parameters for calculating energies and everything in this file, which are seeing in this text editor here. Yeah, if you look down, okay. Yeah, this is the This is how they calculate the angle energy, potential for angle. Yeah, and let me see. Okay, anyway, I think you get the idea. So they have all the energy terms, how to calculate energy terms and different parameters to calculate those energies. This file contains these physical informations. So we'll use these files to calculate the dynamics of our protein system. I'll quit this. Uh, and since I have mm, installed NAMD locally, I'll first show how to run the NAMD in a local computer. I think if you look at the original file here, due to some reason, oh, I think it's back here. Let me show you. Yeah. So this page will teach you how to install the NAMD and the VMD in your local computer. I think it's a good idea because while we submit the job in the supercomputing center, we have to wait till our job, they accept our job and it starts running. So what happens if we make some mistakes while preparing these files, then it's a waste of time. If there is something wrong and we waited for some time and there is something went wrong and we wasted our time. So it's always a good idea to install NAMD and check check locally whether all the set of files and everything, they are up to mark or they are working well. So then after we can submit the job in computing centers, where we can use the facility of parallel computing and other things there. Yeah, we can use their good and advanced technology to make our simulation faster. Also, we can run it for a longer period of time. Yep. So for now, I have already installed NAMD locally. So I'll show you uh, how to run the NAMD locally. So for now, if you remember, we have we set a configuration file that okay, we will output our files to this output directory and the initials of our output will be equal. Oh, I think I haven't completed this explaining this file. Okay, let me quickly go through this file. So I think I discuss about this file. So this is line 31 is the temperature and we set it to 300. And for this simulation, we are using implicit model for the water. So altogether, we have two different water models. One is the implicit model. So this implicit model here we do is what this model does is, so we physically define we don't physically put the waters in the simulation process. Instead, we define the parameters for the waters and ions and everything. So there we use the dielectrics of the water system we use, or the ions we use. So once we call this model, they will automatically define the parameters like their dielectric content, uh, constants and other thing for the simulation. They don't put the real water molecules. Instead, they define the dielectric constant or other parameters to represent water or ions in the system. So it is to mimic, somehow mimic the native environment, because in a native environment, protein is not isolated. It is in some surrounding of some solvents and ions and other different things. So this is to include its surrounding, the ion environment or the water environment. And this environment is not defined explicitly. Instead, we define some parameters to represent those systems. And this is also for calculation of different energy terms. This is the cutoff. So this is the distance cutoff from where this is the distance cutoff, and within this region, we calculate the energy terms, and beyond this, we just simply neglect the energy terms because sometime like the energy terms beyond this region will be very negligible, and including the energy far away could be time consuming, and we need a huge resources to do this. So for the faster calculation and uh, faster calculation, we use certain approximations there. So this is the one of them. So we calculate the energy terms within certain regions and forget about the energy or effect beyond that region. So these things are also included in the paper that I've included in this shared folder here. If you're curious, you can just look at that. Mm, yeah, these are also the switching factors. These are also related to this cutoff, from which point we start to switch, something like that. This is the time step. So if you recall the formula, we use from the Newtonian mechanics that I showed in this PDB file here. So this formula, from here, we'll get the coordinates or other velocities here. So those calculations are done in every 2 femtosecond. This is in scale of femtosecond. So in time scale of 2 femtosecond, we'll calculate once. We'll calculate all the energy terms in every 2 femtoseconds. We can also change it uh, according to our requirement. So for now, I'm using the default value here. Yeah, if the system is very complicated and if it is crashes sometimes, we can decrease this time step to be 1 and get some detailed calculations. Yeah, for now, let's make it 2 here. And these rigid bonds are for, I think it's for the hydrogen bonds. I think it will make the hydrogen atoms the hydrogen bonds to be rigid. Mm, I don't remember what these parameters are. This block is to control the temperature in our system. So we define our temperature to be 300 Kelvin, and this block will help us to maintain 300 degree Kelvin temperature throughout the process of simulation. So I have commented out silent some of the features here. I think I can explain this some other times. For now, we are not using these blocks. Yeah, this is for the restart frequency. So while the simulation is running and somehow if it crashes due to the power shortage, outrage, or something 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 went wrong, then they use a smart way to save certain stages of the simulation, and from where like we can restart our simulation. By doing this, we don't have to like redo everything from the 0 step. So this is to save our process, from where we can restart our system in case of like something happens wrong. So for now, we are like setting the restart points in every 5,000 steps. This is for DCD, and actually this is it will it will be a binary output. So it contains the dynamics of our simulation, entire simulation. This is for position, frequency. This is for energy output. So in every 1,000 steps, we will calculate the energy. It will calculate the energy for every step, but we'll save it in every 1,000 steps. So if we save for the every step, then it will be the output file will be very, very big, and it's not worthy to save every steps. So it will also save some times and memory. So yeah, generally this is what we do to save our time, and resources. Yep. This is the pressure record of the pressure. Yeah. And so in while the protein structure is being solved, so it may not be in the suitable or in the minimum or in the natural position. It can be in different excited states. So if we directly impose the force field and run the simulation, it may crack because it's not in the natural position. So its energy can be in some higher states and it can break. So it's always a good idea to minimize the structure first. So what minimizes does is, so it will bring our system to the minimum configuration, minimum energy configuration, where the systems where the system is naturally occurred, or in the minimum position there, and which is stable by nature. So we'll do some steps for the minimization to get the minimum energy configuration. After we achieve that, uh, we will finally run our simulation for certain time steps. So here we use the time steps to be 2 for a single step. So if you do some math, then as per your requirement, you can assign the run steps here. So for now, I set it to the 1 nanosecond. So it's up to the user how long he or she wants to run the simulation. They can make the calculation and give the number of steps here. Yeah. So yeah, this is all about the configuration file. There are also a lot of other things that can be intake in this configuration file. A lot of advanced things can be done here. This is the simplest example for running the simulation. There are also other advanced things we can do. For example, we can apply certain constraint or fix certain regions of the protein. We can apply some electric fields. We can do a lot of other things. Things things by calling different parameters in this configuration file. We can also apply some user-defined force field or electric fields. We can make use of explicit water models. Yeah, and then many more other things. Yeah. So this is all about the parameter files that we'll be using in the simulation. Let me quit this and let's run the simulation here. If you remember, in the configuration file, we said that, okay, we'll save our output files in this output, this output folder. You can create a directory with this. I already created this, so I won't create again. Even if we create, it will overwrite and delete all the information inside this folder. So we have to be careful while we making these directories. Sometimes it can delete our original informations. Okay, so let's run the NAMD simulation. So to run the NAMD simulation, once you install the package, the program, and type the NAMD 2. So the command to run the program is NAMD 2. Then after we need to supply the parameter file that we created, which is this one. Yeah, and it will give us some. So if we run here, so it starts running. So let me cancel this. It's on-screen output, but we want to save this information. So the way to save this information is to redirect these informations in our folder, which is this folder, and give some name for the, let's say, we'll save all this information in some txt file. So these informations will be saved in this txt file, and the informations and the outputs from the NAMD will also be saved inside this folder, which we define in this configuration file, which is this one. Yeah. Okay, let's run it. So it's running. We don't see anything here. It's writing all the information on this folder. It's already started giving us some output files. So let's look at this this output file. Generally, this is the output file for energy energy terms, and these are the different energy terms. If you see, look at this file. Let's see. Yeah, the file is also being written every time, so it's growing file. So let's go to the end. It has run through 301 steps. Till now, we have 301 steps, and these are different energy terms. Let's see what these different energy terms are. To make it bigger. Okay. So, okay. So this is the number of time step. Currently, this is 300. In this case, this 301 and 390, 299, something like that. So this second is the bond energy. So third is the angle energy, dihedral, improper, electric, van der Waals, and other different energy terms, kinetic and total. These are the different energy terms that we get from the NAMD simulation. So let's quit this and let's check the number of time step that we reached at this instant. So we can make use of some commands to look at the files. Let's see the bottom of the file. We can look at the bottom of the file through the tail command. Let's see. Yeah, now we have 1196 steps, 1200 something like this. Uh, so I think we, in every 5,000 or something steps, we record the DCD files and the energy output files. So this is for the minimization process. So it is giving the output for every step. So once the minimization is completed and we go to the real simulation or the equilibration process, in every 1000 we will see the energy outputs, not in every step, but in every 1000 steps. Similarly, the coordinates and the velocities are also saved in every certain steps that we define in the configuration file. So yeah, for now we have to wait till our simulation has simulation to be finished. Yeah, we just need to wait. I can I've also included, as the time passes, we'll see other output files in this folder. But this is simply the trial. We are not running our simulation locally because we don't have a very good resources to calculate this simulation. It will take a lot of time. So So we will run this simulation using using our supercomputing center resources, and recently we are using TACC, which is at UT Austin, I guess. So they have a huge resources, and we can make use of multiple CPUs, and even we can run the NAMD in a parallel version to make calculation faster. Okay, this is just a trial, and this is a good idea to check the process. If everything works well, then it should be working on the supercomputer as well. So yeah, in this folder, I also included some other sample files there. So maybe, yeah, if you guys are interested, maybe we can continue this lecture maybe next time. In next lecture, maybe I can explain other different things and how to run the simulation in TSCC, how to submit the job, and how to look at the trajectories and do some primary analysis from the trajectories. I think I want to conclude this lecture here. Yeah.
Okay, thank you, Chitra. Excellent. So, anyone has any questions? Okay, so if there's, let me see. Manual is a manual. Okay, actually, I see some questions. So someone is asking if there's a manual of NAMD. Actually, yes. If you do a search of NAMD manual, you will find it. It's online.
Actually, I have included some of the links here. You can look at this. You can read about the configuration files, the NAMD tutorial here, user guide. I have included these things in the info file there. If you look at the info file, you'll get information about these things here. Yeah, about the NAMD and other things too. Yeah.
Okay, great. Thank you.
Mm-hmm.
Okay, everyone, do you have any other questions? If not, we will meet on Wednesday, and on Wednesday, Chitra will continue to give you the more advanced tutorial of NAMD. Okay, then that's it. Thank you, Chitra. Thank you, everyone.
Thank you, Dr. Lee.
See you guys. Bye-bye.
Bye.
Okay, bye-bye.
Bye.